let's take a focus on our BBM92 experimental setup. This is an experiment that we have set up in our BrightNet testbed at the Aliro headquarters in Boston. And the way that a BBM92 setup looks like is like so in this diagram in figure 1. So here we have in the center a entangled photon source. This entangled photon source will emit entangled photon pairs, and those photon pairs are entangled in the polarization basis, where one is horizontal and the other is vertical. Now they're in the superposition where we don't know which is horizontal and which is vertical, and this is our standard entanglement. Now that entanglement will travel down a fiber optic cable and accumulate some loss and then reach the measurement node. Inside the measurement node, we make a passive basis selection using this first beam splitter. So this beam splitter will take the incident photon and send it one way or the other. One way, it'll be detected in the horizontal or vertical basis, and the other way, it'll be detected in the diagonal or anti-diagonal basis. Next, we pass through these polarization control and correction devices, which are wave plates that can be rotated along the optical axis. And what these wave plates do is they first correct any sort of offsets between the two parties or any polarization drift that might have been accumulated during the fiber transmission. And then they also offset the two bases from each other. The idea being that horizontal and vertical basis is rotated off of the diagonal anti-diagonal basis, and these two bases are mutually unbiased and used for key distribution. Now, the polarizing beam splitter then splits our polarization corrected light into one direction or the other based on its polarization. This is where the ultimate measurement basis is being applied, and the measurement then occurs at the detectors. The detectors will register a click at a particular timestamp. We record the timestamps of when each detector clicks, and after we collect lots and lots of data and run this for a long period of time, we'll then go through all of the detection data and reconcile which of those detectors clicked in coincidence across both sides. These coincident counts are exactly what we use to establish a shared secret key. If they came from the same photon pair, then they might then they're entangled with each other, and those detections are correlated. So using these correlated detections, we then will perform key sifting and calculate a quantum bit error rate. So the chance that there is an error in the key that you establish, and the secure key rate, which is the rate at which you can produce secure key without any errors. Now, the two key metrics here, of course, are the quantum bit error rate, which measures the quality of the quantum signal, and then there's the secure key rate, which measures the quality of the key distribution service. Now, these are the standard metrics. They're agnostic of hardware and apply to all key distribution systems that you can run. And the main idea here is you want a quantum bit error rate to be close to 0 because you don't want any errors, and you want your secure key rate to be as high as possible so that you can create lots of keys and use this as a service in a practical manner.